All right, so I've gotten a new microphone. Hopefully that'll get rid of some of the speaker problems here. Um, Today's lecture is going to be a little odd. We're finishing chapter 5 and moving to chapter 6. And we'll probably touch a little bit on the subjects in chapter 6, but there won't be any homework from chapter 6. But in chapter 5, we start talking about sets of numbers. And as you'll see in the discussion forum post, mental concepts come into play here. And as I alluded to anthropologically, natural numbers, developing cultures, from before that, there's the idea of like 1, 2, and I will jokingly always, from a bad Dungeons and Dragons campaign, say too many. How do orcs count? 1, 2, too many. But we seem to find language has that way of numbers, and when we look at the different number sets we have had, there are some number sets that have tally marks and tick marks in their words, where the syllables increase. And so eventually humans invent names for numbers, and those names inside our minds create concepts. Reality is whatever reality is, but these number things have concepts back behind them. Sorry, my cable's making a weird little creaking noise when I write. I'm going to try to minimize that noise for you there. And so those concepts behind the numbers, when you see the number 2, you conceptually think of two things, right? With tally marks. And if I put the number 2 onto an object, let's say, a pail, then I will think, hey, there's 2 of these pails. If we're thinking of counting. But if I attach the number 2 to inches, I think I attach it to the length of something. And so we have different mental concepts based about how we're using the number, even though the patterns underneath it, the patterns that we as humans are putting on them, exist. Right. And the question is, what is reality? I think one of the things that you'll find when you study mathematics or sciences, religions, philosophies, is we're trying to understand a reality that we only get through our senses. And some of the conceptual things that we see and the patterns we see are deeper than what we can immediately divine. And so we're looking for patterns. And so human beings tend to develop natural numbers, and they might actually develop a whole different set of numbers without getting the concept of 0, which goes into whole numbers. And as we noticed from our previous discussion, India was, because of the questions they were asking, were able to use the number 0 quite effectively and create very large numbers, which had a technological advantage. It also has a mental advantage. You can do things in your head with these things once you have the concepts for them. But then we had integers, which gets the set of z, which has negative numbers. Oops. And now we have the mental concept of owing things, or being in debt, or being positionally around some origin or some 0. There's an idea of place. And so this both has a geometry and a counting statistic to it. And then we get integers, or not integers, rational numbers. Z is integers. We get rational numbers, which was our first set where we have to use a creation rule to define it, right? It's A and B, where A and B are integers. All right, and so we get this, and b can't equal 0. And so it's this first set that's built by the creation rule, where the other ones we can kind of list, and underneath it all we can say, hey, this thing is built up by always jumping 1 to the next number. This one says if we start in an origin, we can jump forward 1 or backwards 1. So there's kind of an underlying creation rule here. But with rational numbers, when we make fractions, there's only one thing we can do. We can divide. Of course, we get our other set, right? because there are rational representations of integers, and so rational numbers contain integers. We're going to come up with a new set. Oh, I put R. Please, these rationals are Q for quotient. I'll leave the mistake in. I won't re-record the video, right? Just laugh. R is real numbers, and that's what we're working towards, is real numbers. And I'm going to show you why they're called real numbers now. And so this lecture is going to talk about all these sets. We're going to end with real numbers, and we're going to hint that there are more sets of numbers than real numbers, and that these concepts create mental images. They create a language, and we use them in the language of mathematics to save space in our mind for these. And we'll reflect on this, but I want to talk about irrational numbers, which get the I part in it, and how irrational numbers have no creation rule. The best I can say is irrational numbers are not able to be displayed as rational numbers. That's the best we can do. They are if I can define these things, these are the things that aren't that. And I'll show you where they first came from in Western culture. This seems to be well documented, at least happened. There's no other accounts of other people kind of inventing these things. People find them, but it really does seem that the Greeks first found these. And people have problems with irrational numbers. Historically, you will see that people will work on trying to prove that pi can be represented as a fraction, and that the square root of 2 has a non-irrational representation. I'm going to show you why the problem is us, not the numbers. So what happens is most numbers, any decimal number, 5, 7, I can turn into a fraction, because that's the hundred spot. And so that's saying I have 357 hundredths. The way we write numbers are fractions. And I showed you earlier, if we take a repeating decimal, I can set that equal to a number, and I can multiply it until the repetition goes away. So I multiply that by 10, right, to get that. But this still repeats, so if I subtract the 2, I'm left with 3, because the subtraction parts will go away. And this gives me 9n, and if I solve for n, I get 1/3. And I'm just going through that really quickly, is that we can represent even these repeating decimals as fractions. Now Pythagoras, we think of him as a mathematician in the modern age, but he was really spiritually looking for ideas. And the things he found in triangles were predictive of nature. And because they were predictive of nature, he thought he had found the secret of the universe, more in a religious sense. And I hope by watching some of the videos, you can see that mathematics and religion kind of went hand in hand at different parts in history, because both were trying to find the truth, and mathematics looks for an abstract truth. We'll see when we talked about Cantor and some infinities being bigger than other. One of the things Cantor was looking for is he thought at the end of all of these different sized infinities would be God. Not saying these are right or wrong. I'm not putting any judgment on science or theology, but what I'm saying is mathematics doesn't exist separate from these things. The quest for the truth and knowledge lies within many different fields. There's a completely artistic side of mathematics. Once you get to certain levels in mathematics and you're trying to find proofs, it's more like writing poetry in this language that we've learned. There are tons of art styles that use the geometries. I love Middle Eastern and Islamic art that uses geometries to create beautiful patterns. I love all styles of art, but that's one that ties directly back to mathematics, and we'll see those in the discussion videos. I will try to highlight different versions of that. But what I want to look at here is something that Pythagoras discovered, and they actually murdered someone because of this. Pythagoras had a sect of people that studied mathematics. He believed that perfect frequencies determine things. He noticed that the sounds, when you pluck strings, if the weight hanging on the string to give it tension, like tuning a guitar, was certain ratios of each other, they would make nice noises. And our modern pentatonic music scale is very much related to the scale that Pythagoras came with. In fact, if I take a guitar string and the 12th fret is exactly halfway in between the two, and the 12th fret makes one octave up. And then if I start halving these distances again, I get the fret ratios that determine the notes. And nice divisions of these, even divisions, Pythagorean divisions of these, will make the pentatonic scale. And so the mathematics kind of goes into what's pleasing to the ear. And a lot of that has to do with how the sound waves add and subtract off of each other. And what happens here is the sound waves here perfectly double each other at this halfway ratio, right? Because you get one sound wave that can do this along the string and another one that can do this, and they add and subtract each other. And so when they add and subtract, you get a perfect doubling. So that wave can also exist, and they're called overtones. If I move somewhere else, we don't get that perfection in waves, but we get some other multiple, which creates the other notes. And Pythagoras noted this just by ear, and he related it back to mathematics, because to tune his string, instead of putting frets down, he put weights on them, and then he could measure the different weights. Well, so Pythagoras believed the whole universe was numbers. He wasn't studying math as this science that he thought he was looking into the divine from a Greek viewpoint. In fact, he invented the word philosopher, and I might have said this in another video. I'll keep repeating it. It's a nice little, for brotherly love, because Greeks had different words for different types of love. Philo, like Philadelphia, and sophos, wisdom or knowledge. And what he was saying was he was a brother of knowledge and in love with it, which meant that he was equal to the divine knowledge. And loads of people came to his school, and he taught. Now, one of the things they ended up finding out was that, and he believed everything would be perfect fractions. You would find these beautiful ratios that would tie the universe together. And everything was fundamentally tied together of some principal component of the universe. There was some thing, and everything else was built of ratios of these things. Well, they were examining the square that I drew up there. And if a square has sides of 1 and 1, you wanted to know what the length of it was. And they said, hey, you know what? It's going to be some ratio, some magic ratio in this nice 1 by 1 square. And the Pythagorean Theorem says I can always find the sides of the square, and we're going to be able to write this fraction. But they couldn't find it. And eventually they could prove that there was no fraction you could write for this. I'm going to show you that proof, not because I want you to do the proof, but I want you to appreciate this is provable. And so this was a secret that they kept in their little community. And one of their members told it to other people. He was kind of bragging about, hey, we know this thing. And so they took him in a boat about a mile offshore, or 2 miles offshore, or something like that, threw him off and took the boat back into land and let him drown. And so I'm going to teach you a proof that got someone murdered. So the Pythagorean Theorem says that if I have a square with sides 1 by 1, the diagonal is going to have a length of square root of 2. What I'm going to prove to you is that we cannot write square root of 2 as a fraction. There is no a, b to write it as a fraction. And the proof I'm going to use is, I'm going to proof by contradiction. I'm going to say this is true. So I'm going to say there exists some p over q that is equal to the square root of 2. I'm going to say it's true, and p over q is in reduced form. Right? It's not 2 over 4, it's 1/2. right? I've reduced the form. And these are fair things to say. All right, well, let's play with these numbers, and we're going to use the rules of real numbers that we're going to develop completely in this chapter, and then they'll help us do algebra later. So let me pull this up here. So there's the square I'm working with, and I'm going to prove to you that we cannot write it as a fraction. I'm going to start that proof by saying I definitely can write it as a fraction. And so, well, I don't like the square root thing, so I'm going to square both sides. So if I square this side, I get p squared over q squared is equal to 2. I'm going to cross multiply. I'm going to say that p squared is equal to 2 times q squared. Well, this is nice because p squared is equal to 2 times q squared. And if we think about it for a second, 2 times any number is always even. And I don't know what q squared is, but I know it's a number. So I can say that p squared is always even. Now there is another proof that I can prove to you, but I want you to just trust me on this one, or maybe I'll ask you to research it a little bit more in homework. We'll see how it goes. But if p squared is always even, if some number, I'll still call it if n squared, I'll give it a different name. I don't want our names to mix. So I'll use if m squared is even, then m is even. And this isn't a hard one to prove. You can take 2n and square it, and you're going to get 4n squared. And you can factor it, pull a 2 out, and you'll see that you have some number that's always even. It takes a couple steps, but you can show it. But what I'll say is, let's think about it this way. If my number is even, so let's say 2, so 2 squared is 4. That works. So 4 does give me an even. Let me think of another perfect square that's even. So 4 squared, I'm sorry, this would be my squared side, right? I guess I should put arrows here. They're not equal. And this will be, this is my square root side, and this is my squared side. So 4 squared, well, that's 16. Yeah, that's definitely even. And what's my next even number? 6, 36. So it seems any even number I take it, if I square it, the square is even. And if I think of odd numbers squared, 3 squared is 9, 5 squared is 25. It looks like the opposite holds true. If my number squared is odd, the number it came from was odd. And it's provable, but I'll just leave it there. So this means that p is even, which means I can write p as some other number. And I'm going to write it as 2a, because 2a is always even. And so now I can come back over here and I can rewrite this as 2a squared over q squared is equal to 2. Not too bad. Right, it's doable. Well, where am I going with it? Well, that becomes 4a squared is equal to 2q squared. So I'm going to divide 2 off of both sides, and I get 2a squared is equal to q squared, which means, same argument as above, q squared is even, which means q is even. So I'm going to write q as 2b. And so I can come back to my original idea that p and q was the reduced form of this, and I can say the square root of 2 is equal to 2a over 2b. But look, it's not in reduced form. And I said it was in reduced form. And so this can't be true. And if it can't be true, that means this can't be true. And so the square root of 2 cannot be written as a fraction. But, and here's the really neat thing, I can go out, I can go in any classroom and there's square tiles on the floor, and they can have a length of 1 and a length of 1. That means the length on the diagonal is square root of 2. It's a real thing, and it has endpoints. I, me, us, human beings, just don't have a system to write that number. Right? The square root of 2, if you go to write it out, gets a decimal, that goes on forever. It never repeats. But the problem isn't the square root of 2. The problem's us, right? Insisting that things should be rational. In fact, the words in the English language, rational was, hey, that makes sense. Irrational, it doesn't make sense, came from mathematics. Ratio means fraction. And this proof, some people thought was irrational, or the fact that these things can't be written as a fraction is irrational. And it became a way of talking about things that didn't make sense. But we know this is a thing and we can measure with it. And so what we're going to study is irrational numbers, numbers that we can't write. And there are a couple of them that pop out a lot. Square roots are irrational. Pi is irrational, and pi is the ratio of the circumference to the diameter, right? Because if I ask for the circumference of the circle, it's pi times the diameter. Well, the value of pi is c over d. And so all circles have the same ratio. And that ratio we can't write. It's a endlessly repeating decimal. And there's another one that gets used in finance a lot, E, which is a irrational number, 2.718, something like that. I always look at my calculator to help me with those. And so what this means is we get a new set of numbers called real numbers that contain all the irrational numbers and all of the rational numbers. And then that's everything we can measure in the real world, right? The fact that we can measure the length of the diagonal in the square means it's real. It's tangible. It has I can make you something that's the length of the square root of 2, even if I can't write the number as a fraction. And notice I'm really choosing my words. I can't write the number as a fraction. And I hope that points out that conceptually the problem's with us. Reality is giving us a much more beautiful pattern than our tool of writing numbers gives us. And so we take that into account. And in this chapter, we're going to learn how to deal with the irrational numbers in a way that's consistent. Now, what we'll find later on is there's another type of number that comes about from the idea of the square root of a negative number. We cannot get a real answer from this. And so Euler invented a thing called an imaginary number. In fact, he actually said this is equal to lowercase I. And that generates a set of numbers called complex numbers, which contain imaginary numbers and real numbers. In fact, they're built with an imaginary and complex part. There's the real part, or a real part, and an imaginary part. That's real, and that's imaginary. And when the imaginary part is 0, you get this set of real numbers. And so if we draw like a space of all possible numbers, kind of in a Venn diagram style, right now, as far as we know in the words and the concepts we have, everything is a complex number. But then inside of that, you have things that are just real numbers. And then inside of real numbers, you have irrational and quotients. And they don't overlap. And reals are part of the complex. And then inside of quotients, you have integers. And inside of integers, you have whole numbers, and inside of whole numbers, you have natural numbers. And these contain each other. While the complex, the purely imaginary part, purely imaginary, and the irrationals aren't contained. Right? Real contains all of these, but the irrationals don't contain these. And so it's kind of a hierarchy of concepts as we've learned them. And so keep that in mind when you're doing these things, that, it might seem odd that these things, we have to use this special notation, but it's the best we can do to write them down because they don't fit with what we've done before. And that's problems with us, right? And so what we're doing is we're inventing another way of talking about these things, so we may talk about them, so we may use them, because I can make one even if I can't write it any better than this.